STAAR Review Part 2, Dilations. The thing that we went over with dilations was using a scale factor, what scale factor means in its words, and then finding a scale factor by doing the inverse of what we did to use a scale factor, which is using division. Then we're going over rotations and the rules for the chart. You'll see how to make the chart all over again, as well as how to make the table. Review the parts of simple and compound interest, and then go over the ideas of the real number system. Okay. So when it comes to dilations, there are two ways that this happens. You have your pre-image, and your pre-image can be the letters without the little apostrophe on top, or which is called prime notation, or it can just be another set of letters, and in the problem it'll say like ABC has been dilated to form figure DEF. Okay. I'm just going to make some random points, and let's write them down. So the thing that we struggled with whenever we went over this before was whenever you have the points, know the information that you've got. And let's write down the coordinates. So over here we're going to write A, and that's at -3, +4. B is at 3, 4. C is at 3, -2. And D is at -3, -2. I'm going to switch colors and say, let's use a scale factor. So scale means it's either going to be enlarged or reduced, which means bigger or smaller. Factor is a number that you multiply by. That's going to be represented as a rule. It's going to say like 2x, 2y. That would be an enlargement. Anything less than 1 would be a reduction. So that would look like 1/2 x, 1/2 y. We're going to go ahead and go with this one. We're going to make a figure that's twice the size. So you can type in -3 times 2, or you can substitute it in 2 times -3 and 4, or 2 times 2 times 4. That'll give you new coordinates of -6, 8. Let's plot that. -6, +8. So I'm going to put that as A prime. Or you could just simply look at it and go, I'm just going to double everything that I've got. 3, 4 would end up being 6, 8. So 6, 8. There's your B prime. You can see here that this has gotten bigger. That's good. That's a good sign that we're doing an enlargement. 3, -2 should be 6, -4. And -3, -2 should be -6, -4. So the things to be watching out for are you might be shown a rule like 2x, 2y over here. And you have to choose, was it an enlargement or a reduction? And then you just look at your notation and be like, okay, it got bigger from the original. So I know it's not going to be 1/2. You could also have to choose the coordinates of the image that comes up from a pre-image. So that means you go through the entire process and then you have the coordinates written for A prime, B prime, C prime, and D prime. There's just so many variations of what you have to do and have to know. My best suggestion for going forward with scale factor and dilations is do everything you possibly can and use all the information to your advantage. So let's go ahead and erase the inside shape and work backwards. Okay, so that means that the information that we do know is A prime is -6, +8. B prime is 6, 8. C prime is 6, -4. And D prime is -6, -4. And we're sitting there going, okay, what scale factor was used to get it to A, the original figure? Okay, so we know that we're going in this direction. That means that we started with a pre-image. We're trying to figure out what was used to make it bigger. So that means we went from A, all right, try and keep up with me here. We went from A to A prime. That means it got bigger. We multiplied A by something larger than 1. You have no idea what it was. But you do know the location of A. A is currently at -3, +4. Okay. There's two ways you can think about this. Mathematically, the easiest way to do it is say, okay, I went from A to A prime by multiplying. So that means to go from A prime to A, I would have to divide. Now we already know that we used a scale factor of 2. I just wanted to use an example so you could see how the process works backwards. So look, if you take -3 and you multiply it by 2, like we did, you get -6. Okay, well, what happens when you take A prime, -6, and divide it by -3? You get 2, which is the scale factor we used. So what do we multiply by? 2. Okay, to work backwards, you divide. A prime divided by A. And I'll use another example of B prime, which was 6, 8, and B, which was 3, 4. Okay, so this direction, we did times 2. So to figure out what this was, we divide. And we don't know what it is, that's why we're dividing. So 6 divided by 3 is 2. 8 divided by 4 is 2. The way that you can check this is whenever you find the scale factor, go, okay, if you had 3 over 6, you'd end up with a half. Did this get bigger or did it get smaller? Does a half fit it getting bigger or does a half fit it getting smaller? Do these little self-checks back and forth. It is complicated, but there are so many ways that you can check, plus the answer will be on the page. Just make sure you're doing everything that you know how to do and putting down all the information that you know. Okay, so this was the coordinate plane and how the table gets created. We eventually just took the table and we were able to recreate it, but I'm going to go ahead and go over the entire process for the coordinate plane and how the table gets created. So 0 and 360 is just because it makes a full circle. So you're starting at 0, you go all the way around, you end up at 360. So that's why those are there. What we originally did was we started off with it's going that way as positive, and it's going up, which is positive. Cool. So the next quadrant going around clockwise. So keep in mind this is clockwise. I don't imagine you're going to have counterclockwise because clockwise is going to be enough, but never know. And then it would just reverse the process. So whenever we get there, I'll show you counterclockwise. Next would be going to the right, which is positive, and then down. Then it would be going negative and negative, then negative to the side and up. All Here's the only things you need to remember is x, y, x, y. So you can see that whenever you do a 180-degree reflection, or you do a reflection across the x and y axis, it ends up being a 180-degree rotation. So if you wanted to reflect or rotate 0, that's how that would go. The tricky part is, remember that this ends up flipping. So your x and y end up flipping. You end up with negative y and positive x. So this ends up getting flipped. That will be your 90 degrees going there. So it would take it from quadrant 1 to quadrant 4. 180 degrees right here. Cool, we don't have to do much anything right there. This one's going to flip again. So this is going to flip. This is going to be your x, this is your y. It's going to end up going y is positive and x is negative. This is gone. There's your 270. And your 360 or all the way back would just be your original coordinates. Okay, so how would you fill on the table on this? So all you have to do is know that 0 is going to be x, y, 360, x, y. You know that 180 is x, y. Now all you have to do is remember that 90 and 270 are yx. Okay, now where the heck do the negatives go? All right, so 0 and 360, those are both positive. Those are done. You know that 180 is the complete opposite of 0 and 360, so those are both going to be negative. Check. Your 90 degrees, the first one's going to be negative. So guess what on the 270? The second one's negative. So from left to right, it goes negative, both negative, second one negative. I would highly suggest recreating this table over and over and over. This is just an explanation. That's all. So this is how the table gets made. You can ignore all this stuff. I just wanted to make sure to explain it before. Like I wanted you to know how the table is being made. So this is you doing counterclockwise, clockwise, anything. So you want to know what direction it's going. It says 180-degree rotation. You put the coordinates that need to be rotated in for that. Whatever the x is, do that. If you have a negative x and you're putting it in for negative x, it's a negative times a negative, makes it positive. Simple interest and compound. The tricky things with compound is, and simple, is that when you find simple interest, you're only finding the interest. So we had to go over vocabulary. P, R, and T. P is principal. That's like saying I'm depositing $5,000 into the bank. That's your principal, the amount of money you start with. Whenever you find the interest on that, that would be based on the rate, which is always going to be a decimal. Remember, move it 2 times to the right. Let's see. Sorry, to the left. Boop, boop. There we go. 0.45. And then that'll be the extra money you make off of it. So you deposit $5,000 in the bank. You have an interest rate of 10% for 1 year. Then you'd be getting $500 on top of that. So you'd have an interest rate of $500, which would be added onto your principal. So whenever you find simple interest, it's just interest. To find out the total amount you have, you'd have to add it to the principal. Hopefully that's knocking some cobwebs loose. We had a lot of discussion about that. So I is interest, what you earn from the principal that you deposit. A, which is the thing that compound interest equals, is the total amount. I don't know why it's A. I mean, I guess amount, but just know that whatever you find with compound is the entire thing. You don't have to add that to anything. Like what you find is actually what it is. If you wanted to find out how much interest you earned with compound, you would have this entire answer, by substituting the numbers in for these variables, and we're going to go over all the variables, is subtract the principal from it, and then you'd find the amount of interest you earned. So that's the only tricky part involved in this. The interest rate, you always got to turn it into a decimal. We also went over the way that you could just divide it by 100, because that's what moving the decimal to the left twice is doing, is dividing by 100. Time is always going to be represented in years, so you should always have solid years, no partials. I shouldn't say like 3.5. It may, but at the same time, it's usually probably going to say like something like 3 to 5 years. And n is the number of times it's compounded. That only applies to compound interest, and that's what this chart right here is for, and that is how many times things can be compounded. And that's always per year. So when we're talking about compounded daily per year, that would be 365 times, because that's how many days are in a year. Weekly would be 52, because that's how many weeks are in a year. Monthly would be 12, because that's how many months are in a year, and annually it would be 1. You're going to be dealing with monthly and annually. If they want to see every single student in the state of Texas miss a question about compound interest, they would ask a question about daily and weekly. So go ahead and feel comfortable in memorizing monthly and annually and what that means times compounded. It should be pretty explicit whenever it says it in the question about how many times it's being compounded. Monthly, it might even give you the number. Real number system. All right, so this really is pretty simple when you just understand what irrational means. When you know what irrational means, it means you know that everything else is rational. Irrational would be some sort of square root that whenever you do it, it's not a perfect square, simply put. So like the square root of 7. Okay, so I'm just going to go ahead and pull up a calculator real quick. Let's look at the square root of 7. Calculator. All right. So standard, I want that. Scientific. All right. 7 square root. Yeah, okay, so you're looking at that and you're sitting there going, I have absolutely no idea what I'm looking at. Yeah, no one does. That's why it's irrational. See, look, you see that it has 6, 4, 5, 7, 5, 1, 3, 1, 1, 0, 6, 4, 5, on and on and on. You're not seeing a pattern in there. You know why? There's no pattern. It's something that's going to go on forever, and it's something that's going to be an approximation. There is no solid answer for the square root of 7. The best answer for the square root of 7 is the square root of 7, because whenever you actually try to find the square root, you can't. So it's something that doesn't repeat, because if the square root of 7 was like 2.4444, we wouldn't be talking about irrational, because we could just put it repeats. It doesn't repeat, and it has no pattern. Another great example of an irrational number would be pi. Pi is 3.14 endless, 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 endless numbers. There's no pattern. There's no repetition. It is just a long list of numbers that never ends. Okay? So there's your irrational. That is how that sums up. It's that simple. Rational is everything else. Rational is all the numbers you typically deal with. The reason that you struggle finding the area circumference of circles is because you deal with irrational numbers, which makes things seem like approximations, because they are. So whenever you're dealing with a natural number, that's your like baby counting numbers, 1, 2, 3, 4. The only difference between a natural and a whole number is that it's baby numbers, including 0. Not a big difference. Integer is natural and whole, except it also includes negatives. So negative 4, negative 3, negative 2, negative 1, separated by 0, or 2 actually show you positive and negative. 0 is the neutral number. So this is where it could get a little confusing, I suppose, because if you were to say, all right, the number -2, is the number -2 a natural number? No, because it's negative. Is it a whole number? No, because whole numbers are just counting numbers or natural numbers, including 0. It does not include negative numbers. An integer is -2. It's also rational. So we have a rational integer. Keep in mind that all three of these words are subtopics to what rational numbers are. Rational numbers is a more umbrella term for what natural, whole, and integers are. An example of something that wouldn't be natural would be the number 0. The number 0 would be considered whole, and it would also be considered an integer. So we can put whole number and integer, but it would not be natural because natural numbers are counting numbers that are not including 0. This would also fit under the rational umbrella. So we have a rational whole integer. Both rational, irrational are umbrellaed under the real number system. So the real number system is rational, irrational, and subtopics of rational are natural, whole, and integer. I would say just brush up on what the difference between natural, whole, and integer are and try and classify those. Just write down some numbers and be like, well, what do you think? If you got a question, throw them my way. That is it for STAAR Review Part 2. You let me know what you need. I'm here to help.